So picture this scenario for a second. It's a Tuesday night, and there's a teenager sitting in their bedroom in Nebraska with this cheap, like $20 Raspberry Pi computer.
Right, just a basic little piece of plastic and silicon.
Exactly. And they pull up a command line, they download a repository off GitHub, and suddenly that little plastic computer is running the exact same flight software that is currently literally piloting the Ingenuity helicopter across the surface of Mars.
Which is just wild to think about. I mean, it sounds like the premise for some 90s sci-fi movie.
Yeah, like hackers, but for space.
Right, but that is the actual reality of the aerospace industry today. We have this cultural assumption, I think, that rocket science is locked behind retina scanners and billion-dollar government paywalls.
Like it's all highly classified.
Exactly, but the vault door is just sitting wide open.
It really is. And that's exactly what we're getting into today. Welcome to the Deep Dive, everyone. Today we are exploring a really fascinating source document. It's titled NASA's Top 10 Ancestral God-Level Tools.
Quite the title.
I know, it's great. And we're looking at this massive treasure trove of open source software that NASA has just quietly released to the public over the years.
Yeah, they've been doing this for a while.
They have. So the mission for today's deep dive is to see how these 10 tools basically formed the ultimate starter pack for you to build a virtual space program right on your own laptop. It's not just a list of random software.
No, it's a complete roadmap.
A literal roadmap. Okay, let's unpack this, because I'm just amazed that the very same tools used to design like billionaire-funded rockets are just free online. Why would NASA do this?
Well, we really need to look at the motivation here. NASA isn't just dropping these files online out of, sheer generosity or something.
Right, there's a strategy.
Absolutely. By open sourcing these highly validated, heavily tested tools, they're essentially forcing a standardization across the whole industry.
Oh, interesting.
Yeah, so if you are, say, a new startup trying to build a lunar lander, or maybe a university team designing a CubeSat, NASA wants you speaking their language.
That makes total sense. So they're basically laying down the infrastructure for the next century of spaceflight.
Exactly, and they want everyone building on the same solid foundation.
Which means, if you're listening to this right now, you have access to that exact same infrastructure. So we're going to build a rocket today, step by step, using this source material. Because, you can't just point a metal tube at the sky and light a match.
Definitely not. You would run into engineering roadblocks immediately.
Right. So the very first question you have to answer when you're building a rocket is, what exactly are we burning?
Yeah, that is the foundation of everything. I mean, before you design a single fin or like a single rivet, you need the chemistry.
The fuel.
Right. You need to know your propellant's theoretical limits. And for that, the aerospace industry relies on a tool from the Glenn Research Center called NASA CEA.
Which stands for Chemical Equilibrium with Applications.
Yes.
The source material mentions this is colloquially known in the industry as the mouth of truth, which I have to say is incredibly dramatic for a piece of math software.
It is dramatic, but it's entirely accurate. CEA dictates the absolute mathematical ceiling of reality for chemical rocketry.
So you literally can't beat the numbers it spits out.
You cannot. It calculates things like combustion temperature, gas composition, and this is the big one, specific impulse.
Okay, let's actually define specific impulse really quickly, just for anyone listening who isn't a propulsion engineer.
Good idea.
The way I've always understood it, specific impulse is basically the miles per gallon metric, but for a rocket engine.
That's a very solid way to look at it, yeah.
It measures how efficiently you are converting your propellant into actual usable thrust, right?
It's a measure of efficiency based on exhaust velocity. And the thing is, no matter how beautifully you design your engine bell or, how incredibly advanced your turbopumps are, you can never, ever exceed the specific impulse limit that CEA calculates for your specific fuel mixture.
Wow. So it's the absolute hard limit of physics.
Exactly. It solves for the minimum Gibbs free energy of the chemical reaction to basically hand you the cosmic truth of what that fuel can do.
Okay, but wait. I was reading the background on CEA and the sources, and it says this program was originally written in ancient Fortran code back in the 1970s.
Yes, it was.
So how is that still the gold standard? I'd imagine modern companies like SpaceX with their Raptor engine or Blue Origin building the BE-4, wouldn't they be using something a bit more modern than 50-year-old code?
You'd really think so, right? But consider this, the fundamental laws of thermodynamics do not change.
Oh, sure.
The way liquid oxygen and liquid methane react in a combustion chamber today is the exact same as it was in 1971.
The chemistry is identical.
Right. So the underlying mathematical model in that old Fortran code is effectively perfect.
So engineers today are just, what, stubbornly using 70s command line interfaces, just green text on a black screen.
Well, no, it's a bit messier than that. Nobody wants to actually write in Fortran today if they can avoid it.
I can imagine.
So the modern engineering community did what it always does best. They built a bridge. There is this open source Python wrapper called Rocket CEA.
Okay, a wrap.
Yeah, it basically takes that ancient perfect Fortran math and wraps it up in a modern Python environment.
Oh, that's brilliant.
It is. You can open your laptop right now, type a few lines of Python, and instantly generate a graph showing how, say, changing the ratio of your fuel to oxidizer alters your specific impulse.
So you get all that 1970s precision, but without the 1970s headache.
Exactly. It makes it incredibly accessible.
All right, so CEA tells us our liquid oxygen and methane combination will give us the thrust we need. The chemistry works. But a puddle of exploding fuel on the ground doesn't get us to orbit.
No, it definitely doesn't.
We need to build a vehicle around it. We need the physical shell.
And that introduces our next major roadblock in the design phase, aerodynamics and structure.
Right.
And for that, NASA provides a tool called OpenVSP, or the Open Vehicle Sketchpad. This one was created by the Langley Research Center.
Now, when I first read about OpenVSP in the source material, they called it a parametric geometry tool. And my brain immediately pictured, like, digital clay.
Oh, like sculpting.
Yeah, like you load up the software and just manually sculpt a rocket or a blended wing aircraft with your mouse until it looks perfectly aerodynamic.
That sounds fun, but actually it's more like a highly complex geometric spreadsheet than digital clay.
A spreadsheet. That sounds way less fun.
Well, think about traditional CAD software, computer-aided design. If you use that, you'd have to meticulously define every single curve, every line, and surface completely by hand.
Which would take forever.
It's incredibly tedious. OpenVSP throws that whole paradigm out the window. It is entirely parameter-driven.
So wait, I don't actually draw a wing. I just type into a text box, like sweep angle 30 degrees, aspect ratio 8, something like that.
Precisely. You just type in the engineering parameters, and the software instantly generates the 3D geometry for you.
Oh, wow.
And here's why that is so powerful. It recalculates everything dynamically.
Meaning if I change my mind.
Right. If you realize your wing needs more lift, you don't have to go back and redraw the whole thing from scratch. You just change the span parameter to, say, 18 meters, and the 3D model instantly morphs.
It just stretches out.
It stretches, and it automatically adjusts the internal volume, the surface area, and the aerodynamic profile.
That is incredibly fast.
It is. And then you can immediately export that model into fluid dynamics software to see how the air actually flows over it. Real aerospace companies, Boeing, Airbus, NASA themselves, they use this exact tool for their advanced conceptual design phases.
Like for those crazy blended wing body plane concepts.
Exactly. It's perfect for rapid prototyping.
Okay, so our virtual rocket is really starting to take shape now. We have the specific impulse limits from CEA. We have the sleek aerodynamic shell designed in OpenVSP.
Looking good so far.
But here's the problem. A sleek shell is empty. We have to cram a massive, violently explosive engine inside it. We need to figure out the internal plumbing.
Yes. And this is where things usually break down in a design. You need pumps, you need turbines, and you need valves to feed that fuel into the combustion chamber at ridiculous speeds.
Right. And for that, the sources say we use TMATS, which is the toolbox for modeling and analysis of thermodynamic systems.
That's the one.
No, this one really stood out to me. It's built on MATLAB, and from what I read, the user interface basically looks like you are playing an engineering version of SimCity.
That's a great comparison.
Because you are basically dragging visual blocks, which represent your valves and your turbines, onto a blank canvas, and then connecting them with digital pipes.
It looks very simple and intuitive on the surface, but the math it handles in the background is just brutal. TMAS is specifically designed to calculate dynamic transient states.
Okay, transient states, meaning like not just when the engine is running smoothly at full throttle in space.
Exactly. Steady state is relatively easy to calculate. But what happens in the exact millisecond when a massive fuel valve snaps shut?
Oh, I see. Like when you turn off a faucet really fast in your house and you hear that loud clunk in the pipes. Like a water hammer effect.
Yes, the water hammer effect, exactly. But imagine that happening with highly pressurized liquid oxygen in a rocket.
That sounds like a bomb going off.
It basically is. The pressure suddenly spikes, the temperature fluctuates wildly, the turbines start spinning down, and that changes the pressure in the very next pipe over.
Right? Everything affects everything else.
Right. So TMATS calculates how that single microsecond event ripples through the entire closed-loop system of your engine. It simulates the chaotic reality of thermodynamics.
Which, as the sources point out, sets up a massive conflict in the design process.
Oh, a huge conflict.
Because the aerodynamics team, the ones using OpenVSP, they just designed this beautiful pencil-thin rocket to cut smoothly through the atmosphere.
Right.
But the thermodynamics team, who were playing SimCity with TMATs, they just realized they need giant, heavy cooling pumps sticking at the side to keep the engine from melting into slag.
Exactly. And meanwhile, the structural engineers just want the hull to be made of 3 inches of solid steel so it doesn't snap in half during launch.
So everyone is basically at war with each other.
This is the classic silo problem in aerospace engineering. Departments work in total isolation, and then they have to fight over the compromises.
So how does NASA fix that?
To solve this, NASA relies on a tool called OpenMDAO. That's MDAO, which stands for Multidisciplinary Design Analysis and Optimization.
Ah, the hardcore optimizer.
Yeah.
I was reading about this, and it says it uses AI-like gradient optimization algorithms, which sounds like a very dense buzzword.
It does sound intimidating.
But if I'm understanding this right, gradient optimization is kind of like, imagine being blindfolded on a really rugged mountain, and you are trying to find the absolute lowest valley.
Okay, I'm with you.
You can't see anything, so you just feel the slope of the ground under your feet. If the ground tilts left, you take a step left.
That is a brilliant way to visualize it.
Yeah.
Yes, you just keep stepping downhill, feeling the slope until the ground flatlines in all directions.
Because then you know you found the bottom.
Right. OpenMDAO does that exact thing mathematically, but instead of walking on a 3D mountain, it is walking across thousands of variables simultaneously.
Thousands of them.
Yeah, it essentially forces the aerodynamics, the structure, and the thermodynamics to all couple together into one massive system.
So you just feed it all the conflicting requirements, the thin aerodynamic shell, the giant heavy pumps, the structural stress limits.
Exactly.
And the algorithm just feels its way down that mathematical mountain until it finds the valley, the absolute perfect sweet spot between maximum thrust, minimum weight, and lowest stress.
It completely removes human bias from the compromise. The algorithm might output a rocket shape that looks a little weird or unintuitive to a human eye, but the math rigorously proves it is the most efficient configuration possible.
That is wild. All right, so OpenMGAO has successfully mediated the war between our engineering teams. We have our optimized, perfectly balanced rocket.
The hardware's done.
But right now, it is just a very expensive metal statue sitting on a launch pad.
Yeah.
Because if it doesn't have a brain to read the sensors and actually steer the engines, it is not going to space.
No, it's just a monument at that point.
Right. So we need to transition from hardware design and talk about the flight software that actually flies the ship.
This is where we basically give the hardware its consciousness. And NASA has 2 very distinct philosophies here, depending entirely on the scale of the mission.
Okay, let's start with the big ones.
For the massive, multi-billion-dollar flagship missions, they use something called CFS, the Core Flight System.
Right. The source material calls this the heavyweight Moon OS because it's the actual operating system powering the new Orion crew capsule and the upcoming Gateway Lunar Space Station.
That's right.
But here is where I get a little confused. Let's say I am NASA, right? And I am spending $10 billion on a brand new crewed spacecraft.
Okay.
Why would I use generalized open source software off the internet? Wouldn't I just hire a team to write brand new, perfectly optimized custom code in something cutting edge for that one specific ship?
That's a super common assumption. People think newer is better. But in aerospace, cutting edge usually just means untested, and untested means dangerous.
Oh, because of bugs.
Exactly. Writing custom code from scratch is basically the riskiest thing you can do. Every single new line of code is a potential catastrophic bug. And when you're out in deep space, you have a massive invisible enemy to deal with radiation.
Right, the cosmic rays.
Yeah, high-energy cosmic rays will literally strike the computer chips and flip the ones and zeros in your memory.
It flips.
Yes. So CFS is heavily verified and written in older, highly tested C code because it has decades of flight heritage proving it can survive those high radiation environments without crashing.
It's bulletproof, or radiation-proof, I guess.
Exactly. But beyond just the safety aspect, the real massive value of CFS is its modularity and reusability. Think about a complex project like a space station.
Okay.
NASA might have, say, Lockheed Martin building the life support system, Boeing building the navigation modules, and maybe a European agency building a science lab.
If they all just wrote their own custom software from scratch, it would be a total nightmare trying to get those systems to talk to each other once they're actually in orbit.
It would be impossible. So NASA mandates that everyone builds their software as a module on top of this shared CFS baseline framework.
So it forces compatibility.
Right. CFS provides all the essential core services, the message bus, the file management, the event scheduling. It guarantees that when you plug all these completely disparate pieces together, the software actually works as a unified nervous system.
That is so smart. Okay, so CFS is the heavyweight OS for the massive, complex missions, but then we have the exact opposite end of the spectrum.
We do.
And here's where it gets really interesting. F prime, which is sometimes written as F with an apostrophe.
Yes, F prime, developed by the Jet Propulsion Laboratory.
F prime is a C++ framework built specifically for smaller, highly agile embedded systems. And this is the tool I mentioned at the very beginning of the deep dive. This is the exact software that acts as the brain for the Ingenuity Mars helicopter.
It is. And F prime is an absolute masterpiece of fault tolerance. Because think about it, when you are flying a tiny drone in the freezing, ultra-thin atmosphere of Mars, things are going to fail.
It's inevitable.
And you can't exactly send a technician up there to hit a reset button on the rover.
Definitely not. So how does F prime survive a hardware failure on another planet?
It uses a very strict component-based architecture. So let's say a temperature sensor on one of the helicopter's spinning motors freezes up and starts sending completely corrupted data.
Okay.
In a traditional monolithic software design, that stream of bad data could cascade, crash the entire operating system, and your helicopter just drops out of the Martian sky.
Total mission failure over one sensor.
Right. But in F prime, that sensor is an isolated component. The software is smart enough to recognize that the component has failed. It isolates it, restarts just that specific tiny piece of code, and continues flying the drone using other data sources.
Wow. So it effectively just amputates the bad data before it infects the rest of the brain.
That's a great way to describe it.
And because F prime is so agile and lightweight, you don't need a supercomputer to run it. Like we said earlier, if you're listening to this, you could literally download this Mars-level code today and run it on a simple Raspberry Pi to control a homemade backyard drone.
The accessibility is just unprecedented.
All right, so our virtual rocket has its optimized hardware shell, and we've loaded up the F prime flight software to act as the brain. We are finally ready to launch, right?
Not even close.
Really? Still,
because space is incredibly unforgiving. Before anyone lights a match or pushes a physical launch button, we have to put our digital ship through the crucible.
a virtual test flight.
A brutally realistic virtual test flight. Which brings us to our physics simulator trick.
Okay, trick. This was developed by the Johnson Space Center, and the source material highlights that this isn't just any simulator. It is an Aerospace-grade 6 degrees of freedom physics engine.
Yes, often just called a 60OF engine.
Let's break down what that actually means.
Yeah, please do. So 60OF means the simulation calculates movement along the 3 spatial axes, moving forward and backward, moving side to side, and moving up and down. That's 3.
Okay. And then there's the rotation around those axes, right?
Yeah.
Pitching up and down, yawing left and right, and rolling. So that makes 6.
Exactly. Now, if you're listening, you might think, well, video game engines like Unreal or Unity do that all the time.
Right. Every flight simulator game does that.
Sure, but game engines take massive mathematical shortcuts. They simplify gravity and they simplify collision physics just to make sure the game looks pretty and runs smoothly at 60 frames per second on your monitor.
They prioritize visuals over math.
Right. Trick does not take shortcuts. If a game engine drops a decimal point in its math, maybe a character's foot clips through the floor for a second.
Funny glitch.
Yeah, funny glitch. But if Trick drops a decimal point, it means your virtual space shuttle just sheared apart and burned up under aerodynamic stress at Mach 3.
Because it is a terrifyingly precise math engine. It's tracking the actual structural strain and the heating on every single square inch of the vehicle.
Exactly. To give you an idea of how intense this is, Trick was literally used to simulate the exact physical forces on the International Space Station's robotic arm when it has to grapple a massive, moving supply ship.
Oh, wow.
It calculates the time-stepping physics of metal flexing in a vacuum. It simulated space shuttle reentries, and it was used to simulate emergency abort scenarios for the Artemis program.
Okay, so Trick ensures our rocket won't physically tear itself apart. We survive the launch. But once we are safely out of the atmosphere, We face a totally new problem navigation.
Right. There are no road signs in the void.
Exactly. We have to know exactly where we are and exactly where our target is. And that requires SPICE.
SPICE-E is managed by the Navigation and Ancillary Information Facility over at JPL, and I really mean this without exaggeration. It is one of the most important data sets in human history.
The solar system GPS.
Basically, SPICE-E handles ephemeris data.
Let's define ephemeris. I know generally it means the trajectory of astronomical objects, but what does that actually look like when you load up the software?
It is a massive, dynamic mathematical matrix. It contains the absolute most precise position, velocity, and gravitational influence of every planet, every moon, and every major asteroid in the solar system, down to the exact millisecond.
Because the solar system isn't static. It's moving. So if I want to fly my rocket to Jupiter, I can't just aim at where Jupiter is today.
No, you'd miss entirely. You have to aim at where Jupiter's going to be in 5 years.
And you have to account for how, like, the gravity of Mars might pull you slightly off course as you fly past it on the way.
Exactly, and SPICE-E calculates all of that. It provided the data required to guide the Cassini probe on its intricate, decade-long dance through the rings of Saturn.
Which was incredible.
It was. It calculated the exact atmospheric entry angles for the Curiosity rover to survive landing on Mars. It guided New Horizons past Pluto. Basically, if you are doing deep space navigation, you are pulling your coordinates from SPICE-E.
All right, so knowing where things are is one thing, but actually driving there is another.
Yeah.
We have to plot the physical route and figure out how much fuel that route is going to take.
Yes.
And that is what GMAT does, the General Mission Analysis Tool.
Right. GMAT basically acts as an open source alternative to expensive commercial software like SDK. It takes your SPICE-E data and your rocket's capabilities, and it allows you to simulate a flight path from low Earth orbit all the way to deep space.
And the currency it uses to calculate that path is called delta V, right?
Yes, delta V.
Which stands for change in velocity. That is the actual budget of space travel. You don't measure a trip in miles, you measure it in exactly how much velocity you need to change your orbit.
Exactly. GMAT figures out exactly how much fuel you need for a specific orbital maneuver, and the level of detail is just staggering. It doesn't just calculate basic gravity.
What else is there?
Well, if you are plotting a trajectory from low Earth orbit to the moon, GMAT calculates atmospheric drag from the microscopic wisps of the upper atmosphere.
Oh, wow.
It even calculates solar radiation pressure.
Wait, really? Meaning the literal physical force of sunlight hitting the hull of your spacecraft and slowly pushing it off course.
Yes. Photons have momentum. It's tiny, but over millions of miles, it matters. GMAT accounts for it. NASA used this software to plan the incredibly complex orbits for the Lunar Reconnaissance Orbiter and the TESS exoplanet telescope.
The precision is just staggering. Okay, so let's tie this all together.
Let's do it.
The math is verified by TRIC. The route is plotted by GMAT using the SPICE matrix. The F' code is ready to execute the burns. It is finally time to sit in the mission control room and watch our creation fly.
The visual payoff.
Yes, and for that visual payoff, NASA gives us Whirlwind.
Whirlwind is a 3D virtual globe rendering engine developed by the Ames Research Center.
And what does it actually do?
It is designed to effortlessly layer high-resolution satellite imagery, weather data, topographic maps, and your real-time telemetry into one cohesive visualization.
So when you're watching a SpaceX launch broadcast, which I'm sure a lot of you listening have done, and they cut to those screens in mission control showing that beautiful 3D Earth with a little rocket icon tracking its real-time trajectory across the globe.
It's that visualization.
That is the ultimate flex.
Yeah.
Because the underlying technology powering those screens is heavily based on Whirlwind. It takes all the raw, dense math we just talked about and turns it into intuitive situational awareness.
You can program it to show the rocket's sensor cones, its communication blind spots, and its exact footprint over the Earth at any given millisecond.
So what does this all mean? We've covered 10 different tools today. And what strikes me is how seamlessly they connect when you view them not just as a list, but as an actual pipeline.
The workflow is incredibly clear when you lay it out.
Exactly. I mean, let's recap this straight from the source. First, we designed the fuel chemistry with CEA.
Which gave us the constraints to build the aerodynamic shape in OpenVSP.
Right. And then that shell forced us to solve the internal thermodynamics with TMATs.
And we used OpenMDAO to negotiate the peace treaty between all those conflicting designs.
We gave the rocket a brain using CFS or F'. We torture tested the physics in TRIC.
We found our way in the dark using SPICE and GMAT.
And finally, we watched it all unfold in Whirlwind.
It is an unbroken chain of logic. NASA has taken the most brutal engineering challenges humanity has ever faced, solved them, and essentially handed the blueprints out for free.
It's amazing. They aren't just an exploration agency. They are quietly one of the most generous and important open source software developers on the planet.
They really have democratized literal rocket science for students, for startups, and for weekend geeks.
Which brings us right back to that teenager in Nebraska we talked about at the start.
It does. This software is no longer locked in a vault. It's sitting on GitHub.
And anyone can download it.
And that leaves us with something really provocative to ponder, I think. Well, for the last 60 years, space exploration has been the exclusive domain of superpowers and billionaires purely because the math was too hard and the software was too expensive.
Right.
But if anyone with internet connection and a laptop now has free access to the exact same design, simulation, and flight software that took humanity to Mars, what happens when a generation of brilliant, bored teenagers starts treating aerospace engineering like a multiplayer video game mod?
Oh, man. That is a wild thought.
Will the next great leap in spacecraft design come from a government agency in Houston? Or is it going to come from a teenager's bedroom?
I guess we'll have to wait and see. Keep your eyes on the stars, everyone, and maybe keep an eye on GitHub, too. Thanks for joining us on this deep dive.